Hello and welcome to another Arlington High School Math 4 Honors lesson. Today we're going to be doing Unit 7, Supplement Number 1, Modeling the Motion of a Rocket. This is one of my absolute favorite lessons. My students like it a lot because there's no homework. All we're going to do today is use what we've learned about acceleration, velocity, position, etc. to try to more realistically model what's going on with a rocket. All right, so let's actually kind of take a look at what the motion of a simple rocket would be like. So down in the left-hand corner, right, we've got our rocket. It's giving out some kind of a flame or propulsion. Anyway, whatever, right? And it takes off. At some point in time, of course, what happens is that the rocket just stops, right? Not the rocket, but the ignition stops. And at that point, the rocket continues to go upward until it loses all of its momentum and then falls back to the ground. Let's watch it again. It's not falling, by the way, because it's hitting the top of my computer. Nothing like that. One more time. All right. We want to model that. Okay? We're just going to do one particular problem. So what we've got is a rocket that is fired, and while its engine burns fuel, it experiences a constant acceleration of 4 meters per second. Notice a positive constant acceleration, 4 meters per second. After burning for 60 seconds, that's the length it burns, it then experiences a constant acceleration due to gravity of negative 10 meters per second. And as a little disclaimer, it's actually negative 9.8, but quite frankly, negative 10 just isn't a nicer number. Okay, so the first thing that we're asked to do is write an equation for the acceleration of the rocket and then sketch a graph of it. Why don't you go ahead and try to write a piecewise formula for the acceleration of this rocket. Pause the video now. Okay, let's do it. It's not that hard, but there is sort of like one little question I bet that many people have in their head. Okay, we know for certain that our acceleration is a constant 4, not 4t, just 4 for the first 60 seconds, right? Now, there's a really good question. Should we have the equals there? Should we not have the equals there, right? To be honest, it doesn't really matter, okay? So I'm going to put it there. Then we're going to have negative 10 when t is greater than 60. Now, there's probably actually another endpoint on this, right, when it hits the ground, but I don't know what that is. Let's actually draw a graph of this. Okay. Right, so we have acceleration versus time. This is what's called a step formula, right? The acceleration is 4 for the first 60 seconds. And then it goes down to negative 10. Maybe keep doing that. From there on out. Right? So that's our acceleration function. It's called a step function, meaning that it stays at a constant, then steps down to another constant. It's kind of cool. Okay? But that's it. Again, whether or not we have an open circle or a closed circle here versus here doesn't matter, as long as it's one or the other. It can't be both. Now, I know that that's unrealistic. I do get that. But hopefully that will be one of the only unrealistic portions of the problem. All right, let's take a look at B. It says, assuming that the rocket has an initial velocity of 0, and its velocity function must be continuous, all right, so let's underline those two. An initial velocity of 0, and its velocity function must be continuous. Then we need to find a piecewise formula for the velocity of the rocket, and then we'll sketch a graph of it, label important points on your graph. We'll get to all of that. But right now I want you to pause the video. After the last lesson, you should be able to come up with the piecewise formula for the velocity. Pause the video now and then unpause it when you're ready to take a look at the solution. Okay, let's go through it. Well, we know that the velocity is going to be the antiderivative of acceleration, okay, with these irritating constants thrown in. So I know my velocity is going to be 4t plus c1, when time is between 0 and 60. And then it's going to be negative 10t plus c2 for all times greater than 60. All right. The fact that it has an initial velocity of 0 is going to lead C1 to be 0, right? If you need to, what you could do is you could actually solve that. You could say, well, V of 0 is 0, so you could put the 0 in for V, put 0 in for T, but then what you're going to find is that C1 is 0. So just like we did in the last lesson, what I'm going to do is I'm just going to erase that. It's gone. Okay. Now, because the velocity must be continuous, what that means is that whatever this formula predicts at 60, right, whatever this one predicts at 60, has to be the same as whatever this one predicts at 60. And the key is that is what will give us our C2, right? Just like on our lesson yesterday, 240 equals negative 600 plus C2, and C2 is 840. So I'm going to go back, I'm going to retroactively get rid of this, and I'm going to put this in. All right, let's graph it. This is a little bit trickier, all right, but it's a really neat graph. Because what happens is 4t, right, starts at the origin. We know it's going to end after 60. And all we're getting is this nice linear function. Now, what is this point over here? Well, that is 240, right? Because we've been going at 4 meters per second for 60 seconds, so we get 240. Now, that's where this one has to take off. But this one now has a slope that's negative, so it does something like that. So this is at the point 60, 240. One other point I'd like to find right now is this point. I'd like to really know what time that occurs at, and we'll understand why that is later. Pause the video for a second, see if you can figure out what time that x-intercept or t-intercept occurs on our velocity graph. All right, hopefully you got 84 seconds. It's not that hard, right? We can just set negative 10t plus 840 equal to 0, and when we solve that, we'll find that t is 84 seconds. By the way, please notice, right, that is where the velocity changes from positive to negative. So that's where the rocket changes direction. A lot of people would erroneously assume that the rocket will change direction at this point, but that's not true. The velocity is positive here, the velocity is positive here, so the rocket is going up, right? It's not until we get past 84 seconds that the velocity turns negative and the rocket's height starts to decrease. Okay, we're going to move on and we're going to do the position formula next, so please write down anything that you need to, and then I'm going to clear the text. All right, let's get rid of it. All right, next page. So what I've got at the top of the page now is I've just restated the problem. That's it, no big deal. And I've also included the velocity formula that we just came up with. I wanted it sitting here on the page because we'll need it, right? It says, assuming that the rocket has an initial position of 0, all right, an initial position of 0, okay, we're in red, that's fine, and its position function must be continuous and differentiable, find a formula for the vertical position y of t. All right, well, as we know, again, this will be the antiderivative of velocity. So what I'd like you to do is pause the video right now and see if you can come up with the whole thing. Come up with the antiderivatives, come up with the constants. One of the constants is going to be huge, just absolutely monstrous, all right, and negative. So pause the video and take up to whatever time you need, maybe 5 to 10 minutes, really. Let's go through it. All right. Well, what do we have? The first formula has got to be 2t squared in order to have a derivative of 4t plus some constant. Again, we'll refer to it as C1. All right. Second formula would have to be negative 5t squared plus 840t plus some second constant. Now, this starts to feel like the same song third verse because the fact that it's got an initial position of 0 is going to lead to C1 being equal to 0. Again, if you don't trust me, all you have to do is say, well, y of 0 is 0. Put that in, 2 times 0 squared plus C1. C1 would be 0. Okay, so that constant is out of there. We'll leave the work, though. Now, what we need is we need our C2. Now, just like the velocity, what we're going to recognize is the fact that whatever position this formula gives us must be the same position that this formula gives us right at 60, right? I mean, I just want you to think about this for a moment. If those two don't give the same position at 60 seconds, then what would happen is at 60 seconds, we'd get one height based on 2t squared. And then immediately at 60.000001 seconds, suddenly the height would instantaneously change to some other value that is, in theory, different, right? That can't happen for a lot of different reasons, but mostly just because of physics. So we're simply going to take this 2, and we're going to put in 60 and square it. Now keep in mind that what that is it's the height of the object right when the rocket's engine stops firing. That's what it is, the height of the rocket when the engine stops firing. But whatever, you don't really need to even know that at this point. We're just going to substitute all of these numbers in. Right? Easy enough to solve for C2. But C2 is rather large. I got to look down at my sheet for this. It's negative 25,200. All right? That's amazing. We can now get rid of this. We'll just get rid of it that far. And we'll put negative 25,200. Okay. Now, we could certainly make an attempt at sketching this parabola by hand, and I would challenge you to think about or these two parabolas by hand, I would challenge you to think about what it would realistically look like. But what we're going to do next is we're going to actually look at a way of graphing it on our calculator. And this is really cool. I know I've shown my students before how to graph a piecewise function on the calculator, but other people that are watching may never have seen this before. I have to give credit to a wonderful math science sub that we have at the high school named Hal Lesser. He taught me how to do this years ago. So right now I'm going to bring up the calculator. All right. I'm going to go into y equals. Now I know our independent variable here is x. That's fine. And watch what I'm going to do. Okay, this is kind of tricky. I'm going to put my first formula in, 2t squared, although it'll be 2x squared. But I'm going to put it in parentheses. I know that seems weird, but watch. Parentheses, 2x squared, parentheses. All right. Now watch this. I'm going to put in parentheses. Now I'm going to put in x. And I'm going to go into what's called the test menu. That's where you get greater than, less than, etc. And I'm going to go x is less than or equal to, back out, 60, and then put in parentheses. So take a look at that. I've got 2t squared inside of one parentheses, and in the other parentheses I have x less than or equal to 60. I don't need the greater than or equal to 0, and I'll explain why eventually. Now, strangely enough, I'm now going to put plus. All right. Now I'm going to put the other formula in parentheses. That's going to take me a little bit. Negative 5x squared plus 840 x minus, not negative, 25,200. All right, parentheses. Parentheses. Now I'm going to put x, go back into the test menu, grab the greater than symbol. Okay, get back out, put in 60, parentheses, take a look. All right, weird, huh? Long formula. And now what I'm ready to do is to graph. Okay, now I have to get a good window. So let's go into my window. Okay, obviously I got to have my x window go beyond 60. How far beyond 60? I'm not exactly sure. Maybe we'll need to play around with that. But I'll go 0 to, let's say, 120. All right, who knows? You never know. Now the y window, that's much harder because I don't know what the maximum height of the rocket is. I might really have to play with this. I might have to go into my table and look. That would be a wonderful way of getting a feeling for the y window. All right, but I've played around with this enough. What I'm going to do, believe it or not, is I'm going to use a y window of y min of 0. Actually, maybe I'll make it negative. I'll do y min is, let's say, negative 20. Yeah, it's a pretty big negative, but and watch this. My y max I'm going to put in as 11,000. This rocket really gets up there. Okay, got my window. Good. Okay. Now what I'm going to do is hit graph. Now watch what happens. This is going to take a little while. Isn't that cool? How it transitions between the concave up parabola in the first portion to the concave down parabola. And yes, where it does do that transition is an inflection point. One of the interesting things is that the second derivatives aren't equal at that inflection point, and they're not equal to 0, right? One second derivative is equal to 4, the other second derivative is equal to -10. Isn't that neat? All right, if I get rid of the calculator, there we go, it's gone. I can sketch a little graph. And actually, let me sketch it in color. I should have done that actually originally. I should have had one parabola come up in one color and another in the other. But really, this is what happens, right? For the first 60 seconds, we've got this nice concave up parabola, right? And then, after 60 seconds, it transitions into this concave down parabola, right? It's kind of cool because it keeps going up, but only until its momentum runs out, it hits its highest point, then it starts coming back down. Isn't that a cool graph? I love that because it's exactly kind of what you expect. Okay, I'm going to be clearing this out, and then we're going to do a couple more questions just based on this model, then we're going to be done. So copy down anything you need to. Okay, I'm going to clear it. All right, last two problems. This is fun. Letter D says Earth's stratosphere starts at 10 kilometers. Will this rocket reach the stratosphere? Solve this problem algebraically. Well, best case scenario, in order to figure out whether it reaches the stratosphere, we'd like to know the height of the rocket when it changes direction, right? When it starts to fall. So what is y equal to when the object starts to fall? Now, I'd like you to pause the video and see if you can figure that out. All right? See if you can figure out the height of the object, but do it algebraically. The height of the object when the object starts to fall, or states to fall. That doesn't look like an R. All right? Pause the video. Take as much time as you need. Okay. Well, strangely enough, we actually already figured out when it starts to fall. Remember that velocity? That velocity graph? That looked something like this. It went boom, boom. Now, of course, a lot of students would think this is the time when it starts to fall. Nope, that's simply when the engine turns off. This was the point when it changed direction. In other words, when it started to fall. And what was that? That was 84 seconds. So all I need to do is figure out y of 84. Now, of course, when we look at our position formula, it's pretty clear that 84 falls in here. So whatever, -5 times 84 squared plus 840 times 84 minus 25,200. But, you know, we work out all those numbers. I don't know what they are off the top of my head. And you get 10,080 meters, which is approximately 10 kilometers, a little bit more. So yes, it just barely hits the stratosphere before it starts to fall. Just barely. All right. Letter E. After how many seconds will the rocket return to the ground surface? Solve this problem graphically. We could definitely solve this algebraically. Okay, for the record, definitely we could solve it algebraically. But again, let's visualize, right? Not with the velocity graph. No. Not with the velocity graph, but with the position graph, right? Because what we have is we have this graph, and this is when it's going to hit the ground, right? So we could use the quadratic formula or other methods to figure this out, but ultimately, let's just use the 0 command, all right, on the graph that we have. I'm not going to go through how to use the 0 command. You've seen that plenty of times. Pause the video now, see if you can figure out what time it hits the ground. Then we'll report the answer and finish up the lesson. All right. Well, using the 0 command on our calculator, we find that that time is 128.89989 seconds. To a ridiculous degree of accuracy, 3 decimal place accuracy. I don't know why. We find that the time is 128.900 seconds. All right. So a little bit more of a realistic modeling of a rocket than what you've probably done in the past. I'm going to clear out the text, so write down anything you need to. Okay, here it goes. All right. Well, that's it for one-dimensional motion. We've seen quite a few different lessons on it. Soon, after we build up the mechanics that we need with vectors, we'll be able to then look at two-dimensional motion, where both the y-coordinate and the x-coordinate of an object are changing over time. But until that point in time, we're going to leave motion alone. All right. So this has been another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and until next time, keep thinking and keep solving problems.